Good afternoon, all of you. Okay, today we have learned about work done in stretching wire. It's called as strain energy. Okay, work done in stretching wire, that is strain energy. Okay, when a wire is stretched, some work is done. Okay, when a wire is stretched, some work is done against the internal force. Against the internal force, that is against the internal restoring force acting between particles of wires. This work done appears as elastic potential energy in the wire. What? That is elastic potential energy in the wire. So for this we consider a elastic wire of length capital L, fixed at one end and other end is being stretched by external force F. So this is the L is the length of wire. This small L is the change in the length of wire. A is the area of a cross section of stretched wire. Okay. A is the area of a cross section of wire. Area of a cross section of wire. And Y is the Young's modulus of the material of wire. Okay. What is Young's modulus? In previous lecture we have studied all this studied. Okay. So what is Young's modulus? Is that longitudinal stress upon longitudinal strain is called as Young's modulus. And longitudinal stress means force per unit area, and longitudinal strain means that is change in length to the original length is called as longitudinal strain. Okay, so Young's modulus, we know that is force per unit area divided by change, that is longitudinal strain, that is change in length upon original length. It should be F into capital L into A into small l. Okay, so this is the equation of Young's modulus. So from this we can say that is force equals to what? That is Y into A onto small l upon capital L. Okay. The work done by external force to extend the wire small length dl is given by. So work done. So the work done by external force. By external force to extend the wire by length small l. So extend the wire by small length dl, by small length dl is given by what? That is small work done is equal to force into small displacement, that is dl, small change in length, that is dl. Okay, but we know that force is what? That is y a small a upon capital A into dl. Okay, so total work done. So total work done. So total work done in producing an extension from 0 to extension झाला 0 to L, extension 0 to फायनल लेंथ किती एक्सटेंड झाली तर L. सो कुठपासून तर 0 पासून तर L पर्यंत. सो 0 to L is, so therefore काय करावं लागेल आपण इंटिग्रेशन घ्यावं लागेल 0 to 1 done, total work done that is W. So dW is equal to integration 0 to L y a l into W into H. Okay, so here, so total work done W is equal to, so Young's modulus area small l, that is changes total length, that is L. These are constant. Okay, y a and capital L are constant. So we integrate only these are the constants, so this is get outside. So 0 to small l into dl. Okay, so what is integration? That is L, that is क्या होगा x to the power n, that is x to the power n plus 1 divided by n plus 1. So here power कितना है 1, so इतना है 1 plus 1, that is 2. So l square divided by 2. This is the integration. So y a upon capital A into l square by 2. This is the total work done. This is equation number 1. Okay, this work done is stored. This work done, total work done, is stored as elastic energy. Okay, or elastic potential energy. This total work done, is stored. Total work done is stored as elastic potential energy, that is capital U. So therefore U is equal to y into A upon capital L into L square by 2. Okay, so this equation can be written as 1 by 2 into A into Young's modulus, area of A is equal to area of cross section of R, and Y is the Young's modulus, and small l upon capital L into L. Okay, so this equation can be represented as like this, that is half into A into Y in bracket small l upon capital L into L. Okay, so from this we can say that this half multiplied by, that is stretching force. So stretching force into, that is extension. So in this term is stretching force. Okay, and this is the L is the extension. Okay, so because force is equal to what? We have find out that is force is equal to what? That is y a small l upon a. So this term is should be stretching force. Okay, this term should be stretching force, and this is the extension. So this equation can be written here, that is U is equal to half into stretching force into extension. Also it can be written as that is U is equal to half of, that is Y capital L upon small l, Y upon capital L upon small l into L upon capital L into L. Okay, here this term, that is half, that is y upon L upon small l, is nothing but the stress. Okay, this is y upon L is the longitudinal stress. Okay, stress is the represent the stress, and this small l upon small l is longitudinal stress, that is strain. Okay, and area into the original length, that is what? That is the volume. Okay, this is the volume of the wire. So this is the, this represent the strain. This is the volume, and this quantity represent the stress. So from this equation we can say that is U is equal to what? Here. So what? U is equal to what? Half into stress into strain into volume. Okay. So this quantity, that is elastic potential energy, is equal to half into stress into strain into volume. Okay. So hence electric potential energy. Therefore, this is, because I represent small u. Okay. Hence elastic potential energy per unit volume is U is equal to half of stress into strain. Okay. So what? First we have to ask in exam, that is write down the expression for elastic potential energy per unit volume. You have to write this equation, that is U is equal to half into stress into strain. Okay. This is the elastic potential energy per unit volume. So it is also called as elastic energy density. It is also called as elastic energy density. This elastic potential energy per unit volume is called as elastic energy density. Elastic energy is also called as elastic energy density. Okay. So what we have solved this expression. How can solve? First of all, we consider a elastic wire of length L. So when we apply force, so this is the some work done occurs. So this wire is fixed at one end, and when we apply a force to the other end, then this wire is extended by a length small l. Okay, and this is the area of a cross section area of a wire. So therefore total work, that is the small work done, that is dW is equal to what? That is force into small change in small extensions, that is dl. So this dW is equal to F into dl, and we know that is what? That is F is equal to, that is y into a into small l upon capital L. So put this value in this equation. So we get dW is equal to y a small l upon capital L into dl. So this is the first small extension. So we have taken the complete work done. So therefore total work done is equal to W is equal to y a upon L into integral 0 to L upon dl, because this quantity is constant. So again integrate, we get work done is equal to y upon L into L square upon 2. But this total work done is nothing but the elastic potential energy. So this is represented as U. Okay, so U is equal to AY upon twice L upon L square. Okay, so this equation is written as, that is half into stretching force into extension, that is half into AY upon small l upon capital L into L. Okay, so this L is extension, AY upon small into small l upon capital is the stretching, that is the stretching force. Okay, so from this we can say that is U is equal to half into stress. This again we reform this equation, and we get equation that is U is equal to stress into strain into volume. Okay, this is the potential energy per unit volume. We get half into stress into strain. This is also called as, that is elastic energy density, that is half into stress into strain.